Pleasure to be here. Good afternoon, everyone. It's really hard to go right after Cole. That was a fantastic overview. So I will talk about the status and challenges of astrophysics. In short, the status is we understand the story or different information channels. The challenge is the devil is in the details, and the details has a lot of uncertainties. Okay, so first let's hear about the stories. So first I will talk about the story-like astrophysical formation channels, and I will specifically mention what I think are the main uncertainties, and that's hindering our progress from the point of view of a forward modeler. So from first principles, we try to model something with populations, and then that should match with the observations. There, of course, can be the other way around. You take the observations and you try to fit or try to inform the forward modeling, okay? So I guess Aditya will talk about the other type, okay? And then I will talk a little bit about eccentric compact object binaries, upper mass gap or intermediate mass black holes, and then some uncertainties and possible ways going beyond gravitational waves that can inform the forward modeling. So in principle, in the isolated evolution of stellar binaries, you can, in principle, create two black holes from two massive stars, and then these black holes emit gravitational waves and merge at some point. But in practice, it's not as simple. First of all, the binary must not break. When a high mass star forms a compact object, it loses a lot of mass that makes the binary really wide. And then often these compact objects get a nettle kick. And if you have a very wide binary, it's very easy to break these binaries, okay? On top of that, there are two conditions that are kind of opposite of each other. The binary, if you want compact mergers, the binaries must not merge before they become compact objects. So they need to be separated enough. And remember, high mass stars become very large before they become very compact. So the separation must be very large. But then, after they become compact binary, their separation needs to be short enough so that they merge within a Hubble time, right? And this, of course, the Peters equation is very strongly dependent on the initial separation, what the time delay for the merger is. So this is just an order of magnitude calculation. So here I am showing you the initial separation, and this is the in spiral time in giga-years. And this is basically the Peters equation line. Okay, so anything that's within this pink region below this is Hubble time. Anything in this pink region are interesting to us. Things will merge and perhaps be detected. But if you think of a 10 solar mass or 10 solar mass black hole progenitor, how big it becomes, and if you put the constraint that during the giant phase they cannot merge, then they need to be here. Okay, so you need some magic. We call this magic common envelope evolution. We believe that this happens even not in compact binaries. We have seen common envelope type binaries. So it's very clear that nature does do common envelope evolution. The problem is we do not really understand the details of the common envelope evolution. We typically parameterize it based on this alpha parameter, which is the viscosity and how quickly the orbital energy can be dissipated, and the lambda parameter, which is the coupling between this orbital energy dissipation and the thermal energy of the envelope, and how quickly you can eject the envelope, because once you have ejected the envelope, there is no more shrinking, okay? And just by tweaking these parameters, you can pretty much get any results, okay? That's where the problem is. There is one way to avoid the rapid expansion of the star size. This is typically called chemically homogeneous evolution. I will not go into the details, but the problem there is it is effective only in a narrow parameter space. You typically cannot form black hole mergers with black hole masses that are lowish, and the orbital period needs to be in a very narrow region of parameter space. Also, so if chemically homogeneous evolution is happening in nature, we should be able to see them in nature, and there hasn't been a lot of just chemically homogeneous evolution observed in stellar binaries so far. Okay. Another thing that is universal for any isolated binary evolution channel, that is the eccentricity should be low. So they are low to begin with because there are a lot of dissipative forces that before they become get into the merging configuration, and then as it goes to higher and higher frequency to be detected by LIGO, Virgo, Kagra, eccentricity decays further. There is, of course, the AGN disks. You can form binary black holes inside AGN disks, and they can do interesting quasi-Lidov oscillations with the supermassive black hole there. So this is very rich in physics, but because of the richness of physics, very little constraints, observational constraints exist. So basically, if you think about it, this can do quasi-Lidov, this can do dynamics, this can do all kinds of resonant orbits, migration traps, all kinds of physics that have been interesting for a very long time in the context of planet formation, okay? So fantastic. I will not talk anything more about it in today's talk. The other thing that I am personally very excited about, that is dynamical formation in dense stellar systems. I believe that we understand this channel the most, because a lot of the uncertain physics does not matter. Ultimately, the cluster basically mixes things up enough that you are not sensitive about the initial conditions and details of common envelope evolution, etc. So the idea is very simple. If you have a mix of stars and black holes being more massive, they come near the center. The time scales are such that these can happen hundreds of times in an old dense star cluster. So that would include globular cluster, some slightly oldish young old clusters, and nuclear star clusters, any dense cluster that is older than its relaxation time, okay? Now, what happens after you have collected these black holes? They interact. They do really interesting dances, and typically the more massive object exchanges into a binary, kicking out the less massive object inside the binary. For example, here you are seeing that this blue thing came, kicked out one of the, well, it hasn't kicked out yet. One of the red things will be kicked out, and now we have a binary. The blue one was a heavy one. So in this particular simulation, I used a 10 solar mass black hole with two 1 solar mass stellar binary. So you can form binary black holes via exchange encounters like this, via 3-body binary formation where three single black holes come close enough at the same time. Two gets kept in a binary. The third one carries out the excess energy. You can have gravitational wave capture. You can have quasi-Lidov mechanism if triples form, okay? Once you have formed a binary black hole or a binary neutron star or a black hole neutron star, the orbits keep shrinking via strong encounters, potentially making them merge within a Hubble time. And this process will stop when the binary gets ejected because of recoil, okay? So ultimately, the efficiency at which you can form these binaries, how much you can harden these binaries, and what is the rate of forming these binaries, all of these are dependent on the dynamical properties of the cluster, and it does not care anything about the birth properties of the progenitor that created this compact object. So very quickly, some of the recent results, there is a lot of interest in the eccentricities, in particular in the view of different frequency observation gravitational wave channels. So these are the all different kinds of dynamically formed black holes that you can see. So these will be quasi-Lid of active triples, non-quasi-Lid of active triples. So triples doesn't necessarily mean that quasi-Lid of will make a difference, right? Then few body captures, single captures, ejected binaries, in-cluster binaries, and field binaries. And from here to here, the frequency decreases. You can see that in LVK, most of the things, so this is a cumulative density function. You can see that most types of binary decay the eccentricities. Decigo will be fantastic, or decigo, not particularly decigo, decihertz observation will be fantastic to find out the eccentricity distribution differences in different channels. And LISA will show a large amount of eccentricity from many of these different channels. And curiously, you will see that these captures are absent in LISA, because what we find is it completely jumps the LISA band and captures at a frequency that surpasses the LISA band and only gets activated in the decihertz band. No, it's the same systems that we are just looking at different points. Another thing that is kind of interesting. So what you are seeing here is, as a function of redshift, this is a co-moving rate. And this is for all, and this is for eccentric systems. The blue is coming from binary channels. The black is coming from triple channels. And what you can see is that triple channels, both quasi-Lid of active and inactive, are typically much lower compared to binary channels, both for all and measurable eccentricity channels. And this is for LVK. Now let me very quickly talk about the very massive black holes that we have detected. There is enough evidence, I think Aditya will talk about that a little bit, to believe that there is an upper limit for the black hole mass coming from stellar evolution. And there are two main ways to form black holes with masses higher than that. So one is the repeated black hole merger. So you have two black holes that form another larger black hole through merger, then that captures another black hole, and then that merges again. So this black hole has no duty to be less than whatever that limit is, okay? The other possibility is that you have a high mass star that has a much larger core. It merges with a lower mass star, which has a much smaller core. And together, they create something that has a core that is not beyond the PISN limit, but it has an envelope that is much more than what is expected from a normal star. And as a result, this core forms a normal black hole first, but then this high mass envelope falls onto itself to create a black hole that is beyond the whatever the PISN limit is, okay? Now, of course, star clusters can, you need a star cluster to activate both of these channels. And what we find, so this is one example that we did with one of my students, Ambarish Khurana. So we just varied the binary fraction for high mass stars. So this is one of the uncertain things. We are getting more and more constraints, but it is one of the things that we do not know very well what the binary fraction is for high mass stars. And we find that if you have high binary fraction in high mass stars, some observers believe that this should be 1. All high mass stars should be in binaries, some of the belief is. You see that the collision collapse is effective only if you have high binary fraction in high mass stars. And you can see it again, and that is, this is for early evolution, okay? So these are all coming from collapse of collision products, okay? You see that there is a strong correlation between the number of high mass black holes produced per model and the binary fraction in high mass stars. Also, the highest mass black hole produced is correlated with the high mass binary fraction. And the reason is very interesting. So this is a very complicated plot. So this is the radius axis, this is the central density axis. So I am comparing two models, one with 0 high mass stellar binaries, one with all 100% high mass stellar binaries. And you see that at the beginning, the central density increases, and then the supernova starts that ejects a lot of mass, and then central density decreases. Okay, and all the collisions need to happen here. Okay, and if you have binaries, you just collect them very quickly before this density can decrease, and you can have a lot of collision, which can enhance this. But by the time you go to the overall evolution, the repeated mergers take over, and let me just skip this. And what is the effect? If you are thinking about the LVK results and which channel will produce the high mass binaries in LVK and so on, that will depend on when the cluster formed. So we understand the merger time very well from our models based on the cluster formation time. Okay, connecting the cluster formation time to redshift is less certain because we do not understand the cluster formation time over cosmological redshifts. It's one of the uncertainties here. Okay, so we have started looking into it, and this is a very preliminary results. So we find that for our best fit models, this is the star formation rate from Maddow and Kinson, and this is our cluster formation times. In comparison, this is the El-Badri cluster formation time that most people use. And the benefit of our thing is that it also explains the metallicity spread in the globular clusters we see today in the Milky Way. So another very quick thing. So no matter how many gravitational wave sources we observe in LIGO, it will be impossible for us to connect the progenitor properties to the compact object properties in a model independent way, because we do not see the progenitor usually. So the only way to do this is if we find large numbers of black holes with something that we can see and model very easily. And Gaia gives us a chance to do that. So basically, here you are seeing a cartoon. So first of all, Gaia can astrometrically resolve the wobble of the black hole, or infer the wobble of the black hole from the astrometric motion of the luminous star. On top of that, if the star is close enough to the black hole, there will be deformations in the shape of the star that will give a periodic modulation in the photometry of the star, or the flux of the star that reaches. So using these two methods, we find that there can be many black holes that could be detected. And some of these black holes can have multiple follow-up detection possibilities. For example, a significant fraction of these black holes can be detected both by Gaia photometry, Gaia astrometry, and Gaia RV. Okay. Another very quick thing. So these Gaia black holes, or other neutron stars or white dwarfs as well, the detectability depends on the luminous companion properties. Like what is the magnitude, how precisely we can see the astrometric motion. So the bias is not dependent on the compact object mass. So here I'm showing you what we are finding. So the intrinsic is the field histogram, and observed is the unfilled histogram. And you can see that over a large range in compact object masses, the intrinsic and the observed, I have written observed, but observable, are very similar to each other. And sorry for going over time. I will just list what I think are the uncertainties, and I have given it like common uncertainties for all channels, uncertainties in isolated evolution, and uncertainties in dynamical assembly. Thank you.
Thank you for this very nice talk. We unfortunately have time for only one quick question, if there is one.
Thanks, Sourav. I have a question. It may not be quick, but so you talked about black holes in dynamical scenarios. And I think there's recent interest in having neutron stars that also merge, maybe in such dynamical scenarios because of maybe eccentricity signatures in NSPH mergers or some things like that. So at least from usual astrophysical wisdom, I thought the idea is that neutron stars, you don't expect them to be merging in such dynamical situations. They maybe remain more in the vicinity of such environments, but what do you, if you have comments on this?
So dynamically creating neutron star black hole or neutron star binaries has two problems. One is neutron stars typically get larger kicks than black holes, so retention is a problem. And then second, neutron stars are not much more massive than the typical stellar binaries, so they do not mass segregate as efficiently as black holes. So if you can overcome these two, neutron star assembly can happen. What I have seen, I haven't looked at it for a while, but what I have seen is per star efficiency for neutron star, or neutron star black hole creation is still higher in dynamical systems. It's just not as efficient as black holes compared to, so the efficiency is higher in dynamical systems than in isolated. Because if a kick breaks a binary, that's it in isolated evolution. But if you can retain it in a cluster, then you can play with it.